Thanks for coming today. We're Austin and Ishan. We work at Picnic. We're going to be talking about a project that we've been working on for the past 2 or 3 years called Picnic Calcite Platform. And yeah, let's just get right into it. So Picnic is an online supermarket. We are fully online, no physical locations or anything like that. People order through our app. And that means that we really focus a lot on personalization. So here's some screenshots of a couple features in the app. On the left, we have our search, where the personalization is things like what are the rankings of the items returned to you. We, of course, want to prioritize things that we expect you to be more likely to buy. We also have things like a meal planner, a weekly meal planner where you can pick some recipes. And for this, the personalization is more interesting because we could be looking at things like dietary preferences for your family, what appliances you own, all that kind of stuff. You can imagine this gets quite complicated. So if we look at it in the context of the application, to build personalized experiences that rely on a lot of different data sources, it can get quite complex. So maybe you need to look at something that's stored in a Mongo database, something stored in Postgres, spread across some microservices, and it's just not very fun to build either on the front end or on the back end because you're always reacting to all of these different requirements. So if we look at a very simplified architecture, you might have something like this, where there are business requirements on the left and then corresponding data APIs on the right. And the problem with a traditional setup where you are grabbing your data from all these different data sources is you have very tight coupling. And the problem that we kept running into was there's a new business requirement. Now I need to change the API. And at Picnic, we're always moving very quickly. We're always trying to build more personalized experiences and so on. So that means this happens a lot. And then there's another requirement. And then there's another API change. And what we really didn't like about this is our business teams who want to move quickly started getting bottlenecked by the technical teams. So they would say, hey, I need an API that does this. Then they run an experiment. It didn't work. Hey, I need an API that does this, and so on. So what we wanted to do was introduce a unified data access API. So we push all of the power to the user. They can just have one interface. They grab all the data they want, and they can implement their personalization experiences. But beyond that, we also wanted to provide a data transformation API. So a lot of things are more complex than just grab data from A and grab data from B. Maybe I want to rank, maybe I want to combine the data in some way, and so on. So we started thinking about, okay, how can we solve this problem? And then we realized, hey, SQL is a very popular way to do this. A lot of people already know how to use it. It's very powerful in terms of data retrieval, transformation, and so on. So our goal was to end up with an architecture that looked more like this. So there's going to be some layer. It's responsible for talking to all of these data sources. And then from the application, I just talk to this one layer and get whatever data I want. And that's cool, because I don't need to know about these microservices or this Postgres database or any of that stuff. So then we started thinking about, okay, how can we do this? And then we found this product called Apache Calcite. And Calcite now serves as this intermediate layer. All the content that's presented in our application goes through this for every single page. And we can also talk a bit about what Calcite is. So it's an open source framework. I like to think of it as supporting building virtual database systems. So you're not actually materializing data on disk or anything like that, but you can register tables in a schema, for example, wrapping a microservice. You could wrap a real database table if that's what you want. But what's really cool about Calcite is it does a lot of the fancy things related to executing a query. So there's a query planner, parsing SQL queries, which as you can imagine is very complex. It has a paradigm for the actual query execution, and so on. And we can also talk a bit about the anatomy of a Calcite query and how it's executed. So I'll pass it to Ishan.
Thanks. So let's look at a Calcite query and what happens to a Calcite query as it goes through the pipeline. As Austin mentioned, Calcite is a generic open source framework that allows us to build virtual databases. So it provides us with all the building blocks we need. So we can kind of roughly divvy it up in this way, where we first have a query, it goes and gets parsed, and a query plan is generated, which is an optimized version of the execution plan. And then you pass it and generate a source code, and then the source code is compiled, and then you actually execute it during query execution. So now let us look at each of these steps in a bit more detail. So the first stage is planning. During the planning stage, you have a query that might look like this. And what the planner tries to do is it first converts this query, into a query plan, which is just a tree of nodes. And then each of these nodes is basically an operation, and each of these operations has a cost. So what the planner tries to do is apply a bunch of planning rules, which are basically optimization rules in different steps, and then come up with a plan which has the least cost. So for example, for a query that looks like this, a plan would be something like that. So you can see that there's a table scan, and then on that table scan, you're doing a filter, which is like this calc node or calc operation. Every plan is then converted into source code. So for this plan, a source code could look something like this. This isn't what it actually looks like. This is just simplified. But you basically are iterating over the user orders and then filtering out based on our filter condition. And then the source code is compiled to bytecode. And then you move to query execution where this bytecode is actually executed. This also lets us take advantage of the JIT, which can continuously optimize this as you execute the same query again and again. But then if calcite has all these things, why did we need to build extensions? Well, the main reason we needed to build extensions to calcite is to support real-time rendering in our app, which means that we want to be able to run these queries in real time so that we can offer real-time personalization to our users in the app. So in each of these phases that I just described, we had to add a bunch of extensions. And we'll be only looking over a few of them today in interest of time, starting with query planning.
Thanks. Yeah, so query planning is the first stage of execution. I would argue it's actually the most interesting because this is the question of how do I take this 200-line SQL query and turn it into a plan that actually tells me, hey, how can I execute this and retrieve the data that the user has asked for? As Ishan mentioned, we have added quite some extensions. We're going to be talking about a couple in this stage. The first one I would say is my favorite, which is what we like to call the index API. And for an intro to the index API, we first need to look a bit at how calcite works in terms of tables. So as we mentioned, calcite supports registering virtual tables in a schema. So if we think about the use case of Picnic, an online supermarket, we might have something like the articles we sell. We might have something like the orders that people have placed, maybe the recipes that we have, and so on. You can imagine this gets quite large, and something else that's very important is if we want to keep this general purpose, it should be very easy to add new tables to support your use case. So let's imagine I want to run a very simple query, something like this. I want to know what is the order where the ID is ABC123. As we mentioned, this is not a real table, but it could, in the case of the orders, correspond to something like an order service API. And I want these to be connected, and I want it to be done as easily and as simply as possible. And then maybe my order service API will support doing a lookup by the ID on this API. So this is something that you can already implement in calcite, but it gets quite cumbersome in terms of needing to know things about calcite internals. How do I parse the filters and extract the values? How do I know which API I should call on the service, and so on? And since we wanted to make it as easy as possible for people to add new tables, we wanted to introduce a new abstraction layer. So then if we look at a simplified example of how you could set this up, you can define an index like this. So if my laser pointer works, nice. So you have a column condition, and you've said, I have this order ID column, and if I detect that someone is trying to apply an equals operation to it, I'm going to invoke this code to retrieve the results. And then that code might look something like this. So we're just calling the order service, we've passed in these order IDs, and we're returning the results. And the index API is fully responsible for analyzing the filters of the query, figuring out what values are actually relevant for this index. And something that's also very interesting is it's responsible for choosing which index to use. So you might notice this little integer here, which is the cost of the index. So it's possible to have multiple indices that could be used to fulfill a query, but you want to choose the one that's the cheapest. Because as Ishan mentioned, this is used for real-time rendering in our application, so it's critical that we execute things as fast as possible. And if all goes well, then a response from the service is going to end up looking something like this. So this is a row in our table. We have some order ID, maybe the amount of the order, and the time at which it was placed. And to talk a bit more about planning in terms of the rules that we use to choose what we do and so on, I'll pass it to Ishan.
Thanks. So now let's look at this orders table being used in a query. So in this query, we are doing a join between the orders table and the shipments table. Now what the query planner will first do is create a more naive plan, which might look like this. You can notice here that we're not actually utilizing this notion of index. And because this is something that we added to calcite, we also needed to add rules to support this notion of index and to push the filter that currently in this plan exists on the join level to the table level utilizing our index. So we had to introduce a new planner rule for that, and that which would convert this to something like this. So you can notice that now the ID is passed into the table called orders, and the join implementation has changed. This is also something that we introduced, which is the indexable batch join. What this basically means is that it takes a batch of rows from the left and then passes it to the right. The reason we did this is because if you can imagine that with every endpoint call, there's some network overhead, some service overhead, etc. And we wanted to reduce that by batching. So we introduced this custom join implementation called index batch join to support our custom implementation and this notion of index. As you can see, that this planning phase is quite important for our operations, and also it's quite expensive because we solve one planner rule. We had to add many planner rules like these for our implementation, and all these planner rules are being applied during the planning phase. So we also added a caching layer to ensure that you don't plan excessively and you only plan when you need to support faster runtime of our queries. So now let's look at the execution phase. Over to you, Austin.
Yeah, thanks. Yeah, so we've got the best plan. What do we do now? We want to execute it. And for execution, we also had to add a bunch of extensions to get what we wanted out of it. And we're going to be looking at a specific one today, which we call dynamic join batch sizes. So here we have a very simple query. I have some table on the left. I'm going to scan that table, and then I'm going to join it with some other table on the right. And as Ishan mentioned, since we're using this ID equals index here, I need some way to grab IDs from the other table, this one over here, and feed them into this. And since this is batch-based, the question becomes, what batch size do I use? And we started out with a global batch size of 100, but that's, of course, not always the best one. So if we look at the actual data here, this returns 745 rows, which with a batch size of 100 means that 614 milliseconds and 8 loops to query this, because I have to grab 8 batches of 100 from the left. So then you might think, okay, why don't I just make the batch size very large? Well, the problem in that situation is that you could grab way more data than you need to. Maybe further up the plan, I'm filtering a lot of it out, or something like that. So we thought, can we make this adaptive for all the many different situations that we have at Picnic? If I recall, there are a few thousand live queries running at any different time. So a global solution doesn't really work. So what we did is we started exporting statistics about the query execution. So what data is flowing through the query in production, and then we do some analysis on that to figure out what is a recommendation for the batch size to use for each join in a query. And we then send this back to calcite. So now if we look at the exact same query being executed, but this is after this fully automated optimization process is run, we didn't change anything about the row count, but we're now using a batch size of 800, which is tailored for this join, and it's significantly faster because now we only send all of the data to the right at once. And this has been really a game changer, I would say, in terms of performance. And what's really cool about it is this doesn't require any manual action on the part of the engineering team or the people who created the tables or anything like that. This all just happens once you put it live. So beyond execution, we can also take a look at the experience of developing queries. So as we mentioned, we wanted to make it as easy as possible for our business teams to build new use cases, new personalizations, and so on. So we introduced some tools for that, which we kind of gather and call the calcite playground. And we're going to take a look at a nice screenshot. So this is what it looks like. This was fully built at Picnic, and this is the main UI that people use whenever they are designing and building queries. So we have a query editor with some nice things like autocomplete. There's a schema explorer. You can benchmark queries, get some statistics. And then another very popular one is things like changing the time. So maybe, for example, I want to see how is this going to perform next week? What's it going to display on the homepage? And then this also includes my personal favorite feature, which is the query analyzer. So this is a much larger example of what we were looking at before, where you execute the query, and we actually instrument every single node to detect things like how many rows were flowing through it, what portion of the execution time did it take up, and so on. And this makes it very nice because you can easily find the bottlenecks. So the way it worked before we had this tool is people might have a 200-line query and say, hey, it's too slow, help. But now we've enabled them to figure out a lot more of that on their own, which is very nice because kind of coming back to the original theme, that means that we aren't the bottleneck, and it frees us up to keep building cool new features like this. So now that we've talked a bit about how it works and how easy it is to use, let's also take a look at the impact this has had on Picnic.
Yeah, so as we were talking about before, you had a business team comes with an idea, they have to talk to developers, a lot of back and forth, a lot of time, and a lot of people. But now, one single team or one single business analyst can come up with an idea, prototype their query on calcite Playground to make sure it works right, make sure it has the right latencies, and then put it in our page configurator. And they have created a new personalized experience in the app all on their own. So what does this mean in principle? Let's say a business team or a business analyst comes up with a use case of, hey, on the homepage, I want to show a carousel that recommends fruits and vegetables that are on discount. Now, this requires some personalization because how do you know which fruits and vegetables to recommend? You also need to check which of them are on discount. And then you also have to check that, oh, these fruits and vegetables should be present at the fulfillment center that this user uses. So quite a lot of data, and they can think of a query like this, which is kind of looking at the recommendations table, inventory, also discounts, and making sure that all of this logic works as expected. They try this out on calcite Playground, everything looks good. They put this on page configuration, and now it's live in the app. What does that mean? That means that if you're Miss Pear who lives in Amsterdam, you get a carousel that looks like this. And if you're Mr. Tomato that lives in Utrecht, he gets different recommendations. And this is not just one carousel. This is the entire app. Our entire app is powered by calcite. That means everything is powered by this. You have a bunch of queries running at the same time to deliver such a personalized experience.
Yeah, and to illustrate that a bit more, we're going to look at what is the experience of when you just open our application. So first off, we're going to look at Miss Pear again. So she's opened the app. This is the home page. You can see there's a lot of data. There's this carousel that we talked about previously here. And this is all fully being run through calcite. So everything from the layout of the page to specifically what's recommended and so on is fully going through our system. That means that if we then again look at Mr. Tomato, he opens the exact same page. He hasn't navigated anywhere special or anything like that. We can see, we can see that he then gets the same carousel here, but with different recommendations. And the layout is also fully personalized. So in this case, we also decided via calcite, yeah, we want to put this carousel here. And then if we just let both of them play, you can see that they are completely different. And it's all fully personalized to these users. And then as we move on to what we want to do next, if you could read very quickly, you may have already seen some of these. But we want to do things like improve our cost model. So for example, earlier I mentioned right now it's hard-coded, but that's not great. We want to make it more adaptive, like the batch sizes, to be based on what's the actual data passing through the system. We want to introduce distributed caching for the compiled code. Right now, the distributed caching is only for the query plans. And then we have some other things like recommendations of indices. That would be very nice, because right now these are just added manually based on what people think they need. And concurrent node execution within the query plan. So if it's possible to execute, for example, 2 inputs of a join in parallel, we want to have that as well, because right now things are serial. And yeah, that's it. Any questions? Yep.
How do you do solve security things? Because I imagine that a certain user will be able to see stuff related to them and not stuff related to another user. But you could compile a query maybe where they would get access to other user stuff. So
Yeah.
somewhere in between, you need to check that.
Yeah, great question. So this is something that's also in progress in terms of us making it fully optimal, because right now the engineering teams unfortunately still have to do a fair amount of work for this. So the security in terms of, let's say I have some table and I want to make sure that I can't see your data. Similarly to how the team secures their service, they also secure their table and the permissions are passed through. So for something like a table where I'm selecting the user's orders, in the table it will handle, hey, this is the user that's executing this request, they're only allowed to see that. What we want to do is to introduce a general purpose solution for this, to where we automatically know who's the user, what are the permissions, and that's just propagated through context, and the table author doesn't have to be aware of it.
That's not in there right now.
The fully automated one is not in there right now. The more manual one is how it works right now.
I have also one question. What was the actual problem
Yeah.
you were trying to solve when you started off?
Yeah, so the actual,
It's not
yeah.
very clear to me where it started.
Yeah, so the actual problem is that the business teams at Picnic want to build a lot of different experiences very quickly. They run a lot of experiments, and they're really focused on personalization because, as we said, it's fully online. So we try to take advantage of how that's different from if you walk down to Albert Heijn, it's just the same for everyone. And the problem that we were running into is that they were often iterating so quickly, and that would require a lot of work on the back-end teams, that we were becoming the bottleneck. And we wanted to provide a more general purpose solution so that they can just iterate using this platform that we've built. And that frees up to go build more cool stuff.
Basically, you wanted to make them the developer.
The query developer, I would say. Or I would say the developer of things that, I won't say they're uninteresting, but things that we would not want to be working on relative to building a cool platform like this. Because if it's like, hey, the API grabs fields A and B, and now I want it to grab fields C and D, that's something that's not super interesting in terms of a developer doing the work. So now that kind of stuff is pushed.
And is that performance thing a spin-off then?
Which performance thing?
Well, you're optimizing the query plans and stuff
Yeah.
like that.
This
under
part.
the hood, you're connecting to all kinds of APIs.
Yeah.
Was that a spin-off because it started with the personalization?
Yeah, so it started with the personalization, and then we introduced calcite to start trying to solve the problem, and then we found these points that we wanted to improve. So for example, the query execution statistics and adaptation over time, we started working on that because we were seeing performance problems when we were using the universal batch size that I was talking about here. So we oh, sorry, go ahead.
Yeah, and implementing all these APIs, it's a lot of development work, right?
Yeah, so implementing the APIs that calcite invokes, that's the responsibility of the business teams. And then what they actually have to do in terms of interacting with calcite is they create their table. So that's what we were talking about a bit with the index API. We wanted to make it as simple as possible to just say, I own the order service, I create the orders table, I have this API, I add that index, and then that's it. Beyond that, it fully works.
But if it ends up that, like Picnic says, we're going to work with Jumbo, for example,
Yeah.
They have their own APIs,
Yeah.
then first you need to do the work, and then the business can start using it, right?
Yeah, so if there were, for example, a new data source, then whatever team is going to own that, because we typically own the platform, they would implement a connection to Jumbo, let's say, and then they register their table in our schema, and then from there, it's just part of this large schema with all these tables. So you can join with...
Business teams do this, implementing those?
That's technical teams. So for example, the order service might be owned by a team who manages the order data, as an example. The business teams are responsible for actually writing the queries, and what's kind of nice about it is they no longer know, like, it's that service and it's this service and so on. It's just all in a schema.
The real back-end teams, they actually build the connections and take care that it kinds of gets a table.
Yeah.
And then from that point on, the business teams do their work.
Yeah, so from the point of the data flowing out of the table, let's say, everything beyond that is handled by calcite, and the point where we kind of go up to is writing the query, because of course the business teams, they write the SQL. And that's what we were really going for with, if I go back to the index API, this would be implemented by a business team who owns something like an order service, for example.
Still a lot of technical knowledge needed.
Yeah, so you have, of course, have to know, like, what data source am I going to register? But what was nice about this is this abstracts away a lot of the technical knowledge about calcite. So I alluded to it a bit, but you can already implement something like this just with raw calcite. But for example, if we look at how you implement handling filters, The calcite platform that we've built figures out, oh, these are the IDs, and it just gives them to you. But you need to do that analysis yourself on the filters if you're using the raw calcite functionality. A question?
From the beginning, in my company, we were trying to do something, but it's a completely different approach.
Yeah.
Copy everything, replicate everything to BigQuery, and then let users play in BigQuery.
Yeah.
The end user, and it's okay. It's not real time, but it's near real time.
Yeah.
What's the reason to not do that?
So when you say it's not real time, but it's near real time, what are you?
Near real time is like
Yeah.
a delay of 20 minutes.
Well, I mean, yeah, it really depends. Like, so we have a lot of different data sources, but there are frequently things where we thought like even sub 1 second is critical. Or if we look at specifically query performance, this would be considered extremely slow.
Yeah, but I mean, near real time in the sense of the data is not exactly what so the queries are very fast.
I see. I see. Yeah.
The only reason why you actually query the
Yeah.
original data and not just replicate the data into a central.
I see what you mean. So maybe I can give an example of something where we don't want the lag. If we go back, lots of slides. But if we look at the meal planner, so that's this one on the right, this was pretty interesting because it's something where I referred to what appliances you own. And the user enters what appliances they own, and we save that in our backend. And then when you go to the next page, as an example, and we start recommending recipes, we don't want to recommend something that you can't cook because you don't have the appliance. So even something like a 20-minute lag of a user data update of what we can see in calcite, again, of course, depends on the use case. But for many of them, even when it was a handful of seconds, the business teams came to us and said, hey, this doesn't work for this feature we're trying to build.
You really mean to query to the source data.
Yeah.
Yeah.
I think there was another question. Yeah.
Yeah, I'm wondering if you create such a hyper-personalized environment
Yeah.
for each customer,
Yeah.
how do you sort of persist the environment of said customer? Is it based on a session that the user using the app? Because when you
Yeah.
there's so many variables, I can imagine
Yeah.
the prices a customer sees, for example,
Mhm.
can change during their usage of an app because it's so real time. How do you prevent that?
Yeah, good question. So for pricing specifically, I'm not sure, so I can't talk about like exactly how that works. But our team actually owns something else that we use for storing things like customer preferences and so on. So as an example, I was talking again about this meal planner. So when the user tells us, hey, I own these appliances, we then persist that into a data store, and then our team actually has some auto-generated calcite tables on top of that. So it kind of depends again on the data source because there are many different ones. So things like the prices of products are not in that data store. So it's very situational. But for the things I'm most familiar with, it's actually another data storage solution that our team owns. Yeah.
First of all, I think it really looks cool. It's a nice solution to use SQL for this. I was wondering, it feels a bit like a federated GraphQL.
Yeah.
Could also be a solution for it.
Yeah, it's funny you mention it because we also looked at GraphQL. And it would work for something like this, but the key things that we liked are that, first off, a lot of the people that we work with are already very familiar with SQL. And secondly, SQL has very powerful data transformation capabilities. So I'm by no means a GraphQL expert, so don't hold me to this. But we very frequently have, and I alluded to this a bit, like 200-line SQL queries that are doing very complex operations across the results of these tables. I only have light experience with GraphQL, so I don't know what all it's capable of, but I've never seen something comparable in a GraphQL query to what some of our analysts are doing. But it actually is an exact other solution that we looked at. Yeah.
One last question. Because you implement so many APIs under the hood,
Yeah.
if one of them is not responding,
Mm-hmm.
then kind of the whole chain breaks up. Or
Yeah, so it depends. So maybe we can look again at the orders example. If we click through all of these. So let's imagine that there's a microservice behind this orders table and it goes down or something like that. Then this query, of course, doesn't work anymore, but it's only queries that actually query the orders table. So if I were querying some other table, calcite doesn't actually interact with this service as part of that. The query planner analyzes and chooses which indices to use, and then when we're actually executing the query, it hits the code, so it could execute something like this, order service dot blah, blah, blah. And that could, of course, error out or time out. It just depends on what's going on. And we have some safeties built in, like a global timeout, just as a fallback.
But it just shows an error message in the app then, or?
Well, it's entirely situational. So that's also part of what we allow the business teams to handle, is in the application, if we return an error to you, and there are different kinds, like it's something that may be more transient, like a timeout, maybe you want to try again. Or if it's something like, hey, there's a state failure on the back end, maybe you just want to display, hey, this page isn't working right now. And it's something,
But
sorry.
I'm asking because,
Yeah.
like if you start building joins,
Yeah.
if you pretend this is real SQL,
Yeah.
and you start building joins, and you have like 4, 5, 6 tables
Mhm.
joined in a complex query,
Yeah.
and one of them breaks because the underlying API is not working,
Yeah.
then yeah, I can imagine you have big troubles in your application because you don't know what the business is, what kind of query they are building.
But the assumption here is that if you need 5 different APIs because you're accessing 5 different tables, then if you had a direct API for the same thing, that would probably also malfunction, right?
Yeah, but now you don't.
So I don't
I
see
mean,
that
it's a lot hard. It becomes a lot harder from my point of view
Yeah.
to debug this. Where is it actually going wrong?
Yeah.
Because you don't know what users are querying together, or am I mistaken there?
Yeah, I mean, we have great observability on for our product, and that really helps us with this. And yeah, I mean, and as he mentioned that, yeah, even if you were creating an API, you would have the same problem. So of course, it also comes to the service, the teams maintaining the service, that they also have some graceful degradation. And in cases where, like, let's say you're trying to load carousels in the app, if one carousel is failing to load, you just don't display it. So sometimes you can do graceful things like that.
I'm sorry?
You can also have circuit breakers.
Yeah.
You might be using those.
I think you
Yeah.
guys can
Yeah.
Yeah, no worries. Any other questions? Oh, okay. Sorry. All right, cool. Well, thank you so much.
Cool. Thanks.